So, before I start today's lecture, let me recap what we did in the previous lecture. The first thing was that when you have this p-n junction, then across the junction you have charge density, you have electric field and you have potential variation. So, this is how we model the charge density, negative charge on p side, a positive charge on n side. And then for uniform doping, we take this charge density to be constant in this region as well as in this region. The electric field is then linear and the potential that changes in quadratic fashion. And if you write the electron energy, it is reverse of that potential because of the negative charge, and therefore, the conduction band energy, the valence band energy, they change. On the p side, the energy levels go up, on the n side they go down, and you have this kind of diagram. And potential barrier is created for electrons. If they want to go from this n side to this p side, then this is the potential barrier and they have to cross this barrier if they want to go in this side. And the majority carriers, the more energetic majority carriers, they are able to diffuse, they are able to cross the barrier even though there is this barrier, and that gives rise to this diffusion current from p side to n side. Then you have minority carriers. For minority carriers, the potential difference helps in migration, and that gives rise to the drift current. The electric field drives this current, this is the drift current, and because of the concentration difference there is a current, that is diffusion current. They are in opposite directions, and if you do not connect any battery, then the magnitudes of diffusion current and drift current are equal and there is no current across the junction. But what if you join a battery? So, we discussed that if you join a battery in this fashion, so that positive of the battery is connected to the p side, this is p side, and the negative is connected to the n side, known as forward biasing. So, this is known as forward biasing of this p-n junction. And if this forward biasing is done, then the barrier height is decreased, the depletion width is decreased, both of them decrease, and that increases diffusion current. So, diffusion current increases and that increases non-linearly, but the drift current remains almost the same, because the drift current is caused by the electric field and there is no barrier to these electrons or holes, and therefore, this drift current remains the same, it is guided by the concentration of the charge carriers. So, that is this. So, a net current goes from p side to n side across the junction in forward biasing. And how does that look like if you plot? It goes like this. This is that biasing voltage. So, up to some voltage of this externally applied source, there is almost no current, it is all exponential and non-linear. And once that threshold is crossed, then all of a sudden lot of current goes, and you have to put some devices so that the current does not exceed a limit, so that your p-n junction is not destroyed, and so on. So, these things we talked in the previous lecture, and now let us go ahead. And so, if I plot this bias voltage V here, this is the battery voltage, the voltage that we apply, applied voltage, also known as bias voltage, and positive side is for forward bias. And here if I write I, then as this V increases, I will increase, but this is not increasing linearly, that also we discussed. It does not increase linearly because it depends on how many electrons are at which energy level, and that is not linear, that is not uniform, that goes exponential, depends on temperature and all that. So, you expect a non-linear thing. So, when the potential is small, then generally the current is very small and almost difficult to measure, but then when the barrier height is considerably reduced, suddenly lot of majority carriers will start diffusing and therefore, it suddenly increases like this. Now, at what point you see this visible increase in the current? That depends on what kind of semiconductor it is and what kind of doping concentrations are. But for silicon, this voltage is roughly say 0.6, 0.7 volts. For germanium, it will be less 0.3, 0.35 volts. So, that is the kind of voltage there. So, if you have a PN junction, we call it PN junction diode. If you have this PN junction diode and you apply a external volt in forward bias condition, initially for small voltages 0.2 volt, 0.3 volt, if you have silicon based semiconductor, you do not see any current, and after some 0.6, 0.7 volts, suddenly you see lot of current going in. Now, for any PN junction diode, there is a limiting current which is say rating of that diode. If you increase current beyond that, you can damage this thing. So, if you are using this in circuit, you have to put proper resistances, and the design should be such that after this voltage, when the current suddenly rises, the current should not become very large, and whatever is the rated current, allowed current, the total current in the circuit should remain less than that, otherwise you will have lot of heating and the whole characteristic of semiconductor may get damaged. So, that is about the forward biasing. And what about reverse biasing? You may have already guessed, if you know forward biasing, the opposite of that is reverse biasing. This is P side, this is N side. Remember, your P side extends up to junction and N side also extends up to junction, and this is your depletion region. This whole thing is depletion region. Now, if I connect my battery so that the negative of the battery is connected to the P side, the positive of the battery is connected to the N side like this. Remember, you have a metallic contact, for connections, very important, and this is done at the time of fabrication itself, this metallic contact. So, this is known as reverse biasing, where you have what you have done to the potential barrier, you have increased the potential barrier. Originally, if the barrier was like this, now it is like this. You increase the potential barrier, and if you increase the potential barrier, what will happen? If you increase the potential barrier, this is V, let us say this is X. If you increase the potential barrier, then I diffusion will decrease. Same region, if decreasing the potential barrier increases diffusion current, then increasing potential barrier will decreases. So, this will decrease, and therefore, this current, this forward current, which already was very small. Remember, with no biasing, remember that with no biasing, I diffusion is equal to I drift, and that is typically in micro ampere region. So, already I diffusion was very small in micro ampere region, and it is further decreasing as you increase the potential difference, and then the drift current remains the same once again, and therefore, your net current in reverse direction will be I drift and minus I diffusion, and I diffusion will go on decreasing, starting from magnitude equal to I drift, it is continuously decreasing if you are increasing the potential barrier more and more, and at certain state diffusion current will become almost insignificant, and your final I will be I drift. So, if I plot that part also on this diagram, this is known as VI diagram or VI characteristic. So, if I plot this reverse bias thing also on this VI characteristic, what do you expect on this side? This drift current is I is equal to I drift. So, here 0 voltage, the net current is 0. At 0 applied voltage, the net current is 0 here, I diffusion is equal to I drift, and finally, it will be equal to I drift. In between, it will go from 0 to that I drift. So, that is the kind of thing. But the I drift is of the order of microamperes, whereas this current here in the forward biased is in say milliamperes or so, several tens of milliamperes of 100 milliamperes, like that, depends on what rating you put that maximum allowed current. But this drift current is going to be very small as compared to the forward bias current once you have beyond that cutoff voltage, then this. So, on the same scale it is very difficult to plot. So, generally what people do is when they want to draw this VI characteristic, they put two different scales. If current and voltage, this is, remember, this is applied voltage and this is the net current, this is net current. So, here they will put some scale like this, and this scale will be calibrated or will be shown in say milliampere. So, suppose this is 10 milliampere, this is 20 milliampere, this is 30 milliampere and so on. So, this is all in milliamperes, this is all in milliamperes. So, all these things are in milliamperes on this side. So, this is all in milliamperes, whereas here again they will write as 10, 20 like that, but then this is in microamperes, and then they will draw whatever diagram they want to draw. So, you have this cutoff voltage and then you have sudden rise of that, and this side it is like this. So, this is the kind of drawing one has to do. Now, if I keep on increasing this reverse bias voltage, will the current be constant all through? There is still some kind of threshold, you cannot go beyond that. So, suppose this is the threshold. What does that mean? That if you come to this point, then the voltage, if you increase the voltage further, try to increase the voltage further, then some other phenomena takes place, because of it all of sudden this current, reverse current, keeps increasing very high. So, the current increases in that reverse direction and that becomes a really high current. So, what is this phenomena? This phenomena is known as breakdown. And this voltage at which this happens, this is known as breakdown voltage. What happens here? So, you have this minority current which is giving you that drift. So, this side is P, this side is N. So, suppose you have an electron here and this electron moves in this direction, that is the drift current, right, that is the drift current. The electron moves in this, minority carriers move because of the electric field, that is known as drift current. So, when it passes through this electric field region, this is that depletion region, and remember in this depletion region only you have this electric field, this is the electric field, and the electron is going in this electric field, force is acting opposite to the electric field, and therefore, this electron is accelerated. This electron is accelerated. Now, if the voltage is high and the depletion region is wide, then it can get large velocities, and if the velocity is large, then that can be sufficient to create new whole electron pairs. The energy can be sufficient, this electron, highly energetic electron, can collide with an atom and break the bond there, and therefore, it can create new carriers, and that is how this current can increase very high, and that is known as breakdown. And if the current is under limit, this is reversible when you remove the voltage and everything is all right, but if the current is more than the rated current for that particular p-n junction diode, then it may get damaged also. So, the complete IV characteristic will have a forward biasing part, a reverse biasing part, and then this is the breakdown. So, now let us do some modeling. So, this p-n junction in forward bias shows this characteristic, and this is somewhere something like 0.6 volt, 0.7 volt for silicon. For germanium it will be less, for other semiconductors it will be different. You have many more semiconductors other than silicon and germanium. So, let us say that the resistance, if I talk of resistance, can I talk of resistance? What is resistance? How do you define that? You define it as V by I. In general, you define resistance as V by I. But here, if V by I is not constant, in this non-linear curve, if you see what is V by I, it is not constant. So, that may not be very meaningful definition. So, what we do is that at what voltage we are talking of, at what voltage we are talking of. Suppose I am talking of this voltage, at this voltage. So, at this voltage what is the current? At this voltage the current is this, the current is this, whatever is the value, some value, this is the current. Then if I increase the voltage little bit from here to here, then what happens? The current increases. How much is that increase? So, that increase one can find how much is that increase. So, suppose the current reaches here. So, you have a delta I and you have a delta V. This is the delta I, the increase in current, and here is the increase in voltage. So, if my circuit is around this point, if my circuit is around this point, then I am concerned with this portion only, and then we define what is called as dynamic resistance. And that dynamic resistance is delta V over delta I, delta V over delta I. So, from the graph you can see that this delta V by delta I, if you write, it is very small, because you increase the voltage by a small amount and the current increases to a high value. So, in forward biased, the resistance of the p-n junction is very low, it is small. Whereas, if you look at the reverse bias condition in these areas, what is happening? You are changing the voltage, you are increasing the voltage, of course, in negative direction, and the current hardly increases, current remains the same. So, delta I is very small. So, if you are in reverse bias, delta I is very small, negligible, almost 0, whereas delta V can be considerable. few volts for example, and your current is not even the change in current is not even a microampere. So, in that case if you define R, which is delta V by delta I, this will be very large. So, in forward bias the PN junction offers a low resistance, in reverse bias it offers a large resistance. In forward bias also, if you are above that knee voltage after which it increases rapidly, then you have low resistance, but if you are in that region below that, the resistance is still high. So, to understand the function, what we will do is we will do a kind of an approximate model, and we will assume that in forward bias resistance is 0 and in reverse bias resistance is infinity. Okay. So, in that case what we are assuming is my IV characteristics is of this kind. The resistance is infinite, so no change in current, and here all of a sudden resistance is 0. So, you have large current. So, anything beyond this you have 0 resistance, anything below this you have infinite resistance. Okay. Now, let me talk of applications. So, suppose you have AC source, suppose you have an AC source which gives you power voltage which changes with the time, some V equal to V naught cos omega t type, the kind of power we get in our household. What we need is a DC voltage, for example, to charge my battery of mobile or charge my battery of a laptop or some other application where DC is required, direct current voltage is required. So, conversion from AC to DC, right, conversion from AC to DC is known as rectification. And the unit that does this is called rectifier. And this PN junction diode we call it diode, can be a good or a basic unit for rectification, a good rectifier. Let us see how. Suppose you have a circuit, suppose you have this voltage source, AC voltage source, and then you have these connecting wires, and what we do is we connect a diode here. What is this? What is this triangle that I am drawing? What is this triangle and this straight line that I have drawn? This is a symbol for diode. Okay. We draw a triangle, a horizontal triangle like this, and put a line here and then a line here and then a line here, and this represents PN junction diode. And what are the things? This straight line represents P side of the junction, and this line represents N side of the junction. Okay, and these are of course the metallic contacts. These are of course the metallic contacts where you do this. This is a representation of the PN junction that we had talked in detail. So, here this is P side and this is N side, and then if I connect it to some resistance or something, what will happen? What will happen? if I take the voltage here, what will happen? So, let us try, let us understand what will happen. So, let us draw a graph. Let us draw a graph where I am plotting time here and this voltage here, this is my voltage V. So, this voltage V here. Since it is an AC, what you have is a waveform which will look like this. Will look like this, it will continue. So, the power source, this source here, that is providing me this kind of a voltage. But when this side is positive, because now it is changing signs, your V is positive here, your V is positive here, V positive, this is positive and this side is negative. So, half the time it is positive, half the time is negative. When it is positive, then this side is positive, this side is negative, and this PN junction is forward biased. Why it is forward biased? This is forward biased because your P is connected to higher voltage, N is connected to lower voltage, and that is the forward bias. And in forward bias, under our approximation, the PN junction offers no resistance and the entire current will flow. So, what you will have is, on the other side you will have a current I in this, and if I again plot this voltage, which voltage now I am plotting and which voltage this was our source voltage, and now this is the voltage as received by the resistance. Okay. So, in the positive cycle, when V is positive, then this offers no resistance, and what you have is a voltage which is just the previous one, this one. What happens when you have negative cycle? What happens when your time is here? The voltage becomes negative. So, this plus becomes minus. So, this plus becomes minus here, and this minus becomes plus here. So, now the P side of the junction is connected to the negative of the voltage source, N side is connected to the positive of the voltage source, and now this is reverse biased. And in reverse bias, the PN junction offers large resistance, and therefore, the current is blocked very small, essentially 0. So, here there is no current in this resistance, and therefore, you do not have any voltage on this, and so the voltage becomes 0. And after that again the voltage becomes positive, again that new cycle starts and so on, and therefore, here again a new cycle, half cycle will start, and the voltage will be like this, and this is how it will continue. Okay. So, this is how it continues. So, what has happened? In this resistance, the current is either in this direction or it is 0. So, at least the direction part has been taken care of. It is not a very good DC. A very good DC means you should have a constant voltage like a battery. So, this is certainly a very bad DC, but it is DC in the sense that the current is not reversing direction, either it is going in one direction or it becomes 0. So, that is how the basic unit of rectification, going from both directions to a single direction, going from changing direction of the current to a same direction in current, can be taken care of just by one PN junction put in the circuit. So, that is the kind of, now this is known as half wave rectification. So, this is known as half wave rectification. Why? Why half wave? Because half the time it is 0, it is doing nothing, half wave rectification. Now, before going further, let me do some experiment and show some of these things qualitatively, how this reverse bias or this forward bias or this rectification takes place in a real circuit. So, let us do some experiment. Here I have a setup in which this is a heater coil, which I will be using as an extended resistance, and on this heater coil I will be putting this 9 volt of battery. So, one end is connected here, one end of the battery is connected here, and the other end of the battery I will be connecting here. So, if I join this, this whole 9 volt is now dropped on this coil. So, if I take a smaller length, I will get a smaller potential difference. If I take a larger length, I will get a larger potential difference. So, now I have a variable source of variable voltage that I can apply. So, the first, let me show you what happens if I connect some kind of a meter, a galvanometer, to this voltage and see how it works. So, I have this galvanometer, and these are the two ends. One end let me fix at one end. So, I am putting it here and it is fixed, the other end. Now, if I want a very small voltage to be given, remember this is galvanometer, very sensitive instrument. So, if I just touch it here, see what happens. Okay? So, it deflects. So, in this small length of heater coil, there is some voltage which is able to deflect this needle. Okay. If I take a larger length here, the deflection is much more. Smaller length, deflection is small. So, it shows that as you take larger and larger length, you have more and more potential drop here. Now, let me put a diode in this circuit. So, let me put a diode here in this path, and where is my diode? This is the diode. Okay, so, let me put it here. This is the diode. We had made diagrams, varieties of diagrams. We had drawn rectangles, and then we had shown some lines, depletion region, this, that. But if you go in the market and ask for a diode, what they will give will look like this. This is the kind of thing. You have this black thing here, then these are two connecting wires which are there. You can see a silver line here, a ring type line. So, that shows which side is P and which side is N. So, this diode I will be connecting in this circuit. So, let me do that. So, now I am connecting the diode to the galvanometer, one end, and the other end of the diode, let me put it here. So, I have connected diode, and this end of the diode I am connecting to my, say, 0 of the voltage source, and this is the other end. So, let me try to apply some voltage here. So, see what happens. I am touching it here. I am touching it here. Did the needle deflect? Did the needle deflect? This needle? No. I am increasing this length. I am touching it here. So, I have applied larger potential difference. Did this needle deflect? No, does not seem to be. Let me go ahead. No, here you can see a slight deflection. Here you can see a slight deflection, and if I go for larger voltage, see what happens. See what happens. So, you remember our VI characteristic. In the forward bias, if I apply a small voltage, very negligible current goes. and once that knee voltage is achieved, after that it goes rapidly. So, that you are seeing here. If I connect this across a small length, I am applying a small voltage. Remember, this is in forward bias, and if I increase the voltage, nothing changes, almost nothing changes. I increase it further, I increase it further, and somewhere it starts deflection. This is that point. For silicon I told 0.6 to 0.7 volts. So, that is this point. Of course, this is not silicon. So, and after that, if you increase the voltage, see, I am increasing this distance. So, I am increasing the voltage and this current is increasing. So, this is one part of the experiment that I wanted to show. So, this was forward bias. Now, let me go for reverse bias. So, if I change the polarity of this PN junction, that will do. So, I will be just opening it here and reverse the polarity. So, I have opened it, I have opened it, I have inverted it, and again I am connecting it. So, this goes in reverse bias. Now, in this reverse bias, I will be applying voltage. I apply a voltage here, look at this needle, is there any deflection in the needle? No. I am increasing the voltage, I am increasing this voltage, nothing happens to this needle. I have increased it this much, nothing happens to this much, nothing happens to this, and so on. So, in the reverse bias, if you apply even large voltages, you should not apply voltage more than the breakdown, but you have seen that I have applied reasonably large voltage here and there was almost no current, at least not visible in this instrument. So, reverse bias almost 0 and forward bias, after that knee voltage it goes up. So, now in this setup you can see several things here. Essentially this is an AC power supply, and I can change the frequency of this AC by this knob. This knob can be rotated and that will change the frequency. I can change the amplitude of the voltage. For that you have this knob here, you can see a line here, blackish line. So, if I rotate this knob, then the voltage, the amplitude of that voltage will change, and the voltage is actually obtained at this point here. So, you have two wires in fact in this cable which are connected to some circuit, and here you are getting that final AC voltage here at these 2 points. So, you are getting your AC supply here. To see that, let me put this galvanometer, bring this galvanometer once again, and I connect this galvanometer to this power supply, to this AC source, and put this on, and you can see the AC. You can see this needle. Can you see this needle? It is going towards left, it is going towards right, and with a very small frequency, very small frequency. I can increase the frequency using this knob. I am increasing it, and see now it is going with somewhat larger frequency. So, this is our AC source. At these 2 points, the voltage is changing its sign, positive, negative, positive, negative. So, let me disconnect it here and put a diode in between. Remember, you had a AC voltage source, and then if you put a diode and then connect it, the diode will pass the current only when it is forward bias, and it will stop the current when it is reverse bias. And if the voltage is continuously changing its sign, half the time it will give a positive voltage, half the time it will give a negative voltage, and then you have half the time diode will pass the current in one direction, and other half of the cycle it will just stop the current. So, you have current in one direction only, but intermittent. So, let me do that. So, once again the same diode which I had used, and this diode I am connecting in this circuit. So, this diode I have connected in this circuit in between, right, and see what happens when I give the amplitude. It only goes in the right direction and then stops here. It goes in the right direction and stops. It is not going in left direction. Half the time there is a current, half the time current is 0, but the current is only in one direction. So, that is that rectifier action that we had discussed, right. Now, let me reverse the polarity of the diode. What do you expect? Since this is AC, it will still work, but what was positive cycle will become negative cycle and vice versa for this diode. That in the halfway when it was forward biased, now it will be reverse biased. So, let me do that. So, I have opened this diode, I have inverted and connected it again. So, now see when I give the voltage, what happens? It goes in the left direction, your needle goes in the left direction, unidirectional, but the direction has changed because I have changed that polarity of this diode, and therefore, what was forward biased earlier has become reversed bias and vice versa. So, what we did on the table? We made a half wave rectifier, and what was that? We had this circuit, we had this voltage source, AC voltage source, we had this diode, and then in place of this resistance we had the galvanometer. So, let me draw it again. We have this voltage source, AC voltage source, I put a diode here, and then if I put some resistance or some meter or anything here, then I get a voltage here which is of this type, This is half wave rectification. What we are plotting here? We are plotting here voltage and time. Which voltage I am plotting? This voltage which appears here between these 2 points, which I had put a galvanometer in place of this resistance, but then that voltage drove that galvanometer and we saw the deflection. So, this is this voltage that we are plotting. This is our half wave rectification, current goes only in one direction. Now, what happens if I put a capacitor here? Suppose I put a capacitor here, what will happen? Suppose I put a capacitor here, and let us say this is point A here and this is point B. Now, this picture will change. So, let me remove this picture because of this capacitor. First, let me draw the potential which is at point A. So, at point A, V at point A. What is this potential? I am taking this as the 0 potential. So, this 0 is right from here to here, this is all 0, this is all 0. So, this is 0 and this at A point I have V A. This is just output of this AC source, and so it will be like this. So, it will be like this. And now, next I plot the potential at point B, VB, as a function of time. What will happen when this voltage increases? This voltage increases as a function of time. This voltage increases. the diode is forward biased, and therefore, it allows current to go, and that current goes in this capacitor as well as in this resistance, and hence the capacitor will get charged, and once the capacitor gets charged, it will charge up to this maximum. So, up to this time, let me draw a line to show the time to some extent. So, up to this time, this voltage is increasing, R into I is also increasing, the capacitor voltage is also increasing, is same, and it goes like this. Now, the voltage is decreasing, VA is decreasing. So, this potential has decreased. You do have a charge on this capacitor, and therefore, that voltage is there, that voltage is here, and this is larger and this is smaller. So, it gets reversed bias here itself. So, in this positive cycle itself, the remaining part of the positive cycle, this part, in this part, in this part, it is already reversed bias, and therefore, this diode stops conducting current. Then what happens? Then you have this RC circuit. So, you have this charged capacitor, and then so this charged capacitor will get discharged through this circuit, through this RC circuit. I hope you remember this RC circuit. If you have a capacitor, charged capacitor, and then a resistance is connected across, the charge will decrease on the capacitor, the voltage will decrease on the capacitor, and that decrease will be governed by the time constant. You remember what is time constant? Now, I am talking of a circuit where you have a capacitor and you have charges here, some charges Q minus Q, and you connect this to a resistance. Then as a function of time, the voltage or this Q, that will decrease exponentially, it decreases exponentially. This is time and this is, let us say, voltage across the capacitor, and then the time constant is given by R times C. So, the voltage decreases like this. So, here also the voltage will now decrease, and it will decrease exponentially. So, it decreases exponentially. So, the voltage decreases fine, your VA also decreases, becomes negative, all right, and at some point of time again it starts increasing, the voltage starts increasing here, the voltage starts increasing, and this side it is decreasing, this side it is exponentially decreasing. So, maybe at some point of time this voltage at say this time, let us say at this time, this voltage here and this voltage here, suppose they become equal. Suppose they become equal. In this drawing it is not like that, but suppose it is equal. I can draw another curve. So, the capacitor voltage was decreasing, at this time they have become equal, and after that the voltage on A side, voltage here is now increased further, the diode becomes forward biased. I am talking of this part. In this part what is happening? In this part the capacitor voltage was decreasing, but then the voltage which is at point A, at this point on the P side of this PN junction has increased, it has increased here, and therefore, it becomes forward biased, and therefore, once again the same story, forward bias. So, the current will flow and the capacitor will get charged, it will get charged up to the maximum, up to here, let us say, up to this time, the capacitor will get charged, again the voltage on this will increase and it will increase to the maximum value. Once it increases and reaches this maximum value here, after that the voltage on the P side decreases, this VA, remember this is VA. So, here the P side voltage decreases, the diode becomes reverse biased, once again discharging starts and this whole cycle will continue. So, it will discharge again like this, once again it will become equal somewhere here and after that again it will be charging and then discharging and so on. So, it will charge and then again it will discharge and so on. So, compare this with the case when we did not have any capacitor. At that time the voltage diagram at B was of this type. This was VB as a function of time and now it is this, and you can see that it is a better DC. This was a very poor DC, very bad DC. It was unidirectional, but if you look at the voltage, far from that ideal constant voltage situation. You have this voltage which is going up, coming down, becoming 0 for a lot of time, again going up, coming down 0. Compared to this, see this voltage here, see this voltage here, compared to that it is a much better DC. So, putting this capacitor here, it is a kind of filter, it is a kind of filter. It makes your DC a better DC in the sense that fluctuation about that average DC is reduced. So, this is this kind of there are more circuits, better circuits, more refined circuits which can make it even smoother. When you are using your chargers for mobile and laptops, you cannot afford to have this kind of bad DC. So, the circuit there does this filter business and makes it much smoother. So far we had been talking of half wave rectification. In half wave rectification, what we have is that the diode which we are using, PN junction diode which is using, is active only half the time and therefore, your final output is like this. Of course, you can do filter and all those things. Now, it is possible to have a full wave rectification. Full wave rectification, that means in your resistance the current is going all the time in the same direction. So, that is full wave rectification and the procedure is simple. We will be showing it using a transformer. This is the symbol for transformer. This side is your input and this side is your output. And if you have a point at the center, you have 3 leads, one coming from top, one coming from center and one coming from this bottom, 2 edges of the coil. This kind of transformer is known as center tapped transformer. And if you take this as 0, if you take this middle one as always say V equal to 0, I will take here, then this will be positive, this will be negative. After half cycle, then after half cycle you will have this as positive, this as negative and so on, it will keep on oscillating. Now, consider this circuit. You have put a diode here, put a diode here, then put a diode here and connect them together, and then you connect your resistance here and think what happens when you have this kind of voltage at this end between these 2 points. Your voltage is like this. So, at this end let us say this is 0 and this is say positive. At certain instant let us say this is positive and this is negative. So, what will happen? This diode, upper diode is forward biased. this diode is forward biased, and therefore, that it will allow the current. This lower diode is reversed bias, it will not allow the current. So, the current will go like this, and then no current in the lower diode. So, this current will return like this, and then this is the circuit, this is the circuit which will be operating. What happens in the next cycle? When the upper point becomes negative and the lower point becomes positive, then what happens? So, suppose now this becomes positive and this becomes negative. So, if this is positive, this is V equal to 0 at the center and this is positive here. So, this diode is now forward biased, this is forward biased, and this is reverse biased, this is negative, remember this is negative here. So, this is reversed bias, and therefore, the lower diode will conduct in this figure, current will go like this, no current through that upper diode. So, what will happen? The current will go through this lower diode and then it will return through this resistance, and once again in the resistance the direction of current is same. So, as far as this resistance is concerned, you have current always in the positive cycle also and in the negative cycle also, positive cycle also, negative cycle also. All the time you have current in this resistance and in the same direction. So, you will get this kind of output. This is known as full wave rectification. This is known as full wave rectification. Okay. So, this is how the center tap transformer will look like. This is the input side where you have 2 wires and then this goes in the main power AC, and on the output side you have 3 wires. You can see here there is a yellow wire in the middle and then you have blue wires at the ends. So, this yellow one is coming from the center of that coil and that is connected here internally. So, this is that center tap point, and then on the sides you have 2 points, one connected to this end, one connected to that end. So, this is that center tapped transformer. So, if you want to connect things, connect it here, this is your 0, this is your V equal to 0, this one is V equal to 0. Then you can put more connectors, you can put the connector here, you can put the connector here, and then you can make your circuit. You can connect a diode here, you can connect another diode here, and these 2 diodes can be connected among themselves. And then the junction of that diode and the center tap, you can put a resistance. You can put a resistance here. So, I can join it here together with this and your full wave rectifier is done.